Hello everyone, welcome to the first and this week's talk in NSE517 Radionuclides in Life Sciences class. We will be talking about a paper titled Production of Novel Diagnostic Radionuclides and Small Medical Cyclotrons by three authors that I'm not sure how to pronounce their names and I don't want to be rude. We will be breaking this paper down into two main categories as shown. Cyclotrons on the industry, which is more about the technology and industry as a whole, and second, being produced isotopes as discussed within the paper. So to start, cyclotrons and the industry. My name is Wyatt Flukiger, and hopefully this will be helpful and answer questions people have. And if not, my partner and I will do our best afterwards to do such in the provided forum. Starting off with the industry needs presented. They were broken down into two main uses, being that of diagnostic and therapeutic radiopharmaceuticals. To define these, generally would have diagnostic as discovering an illness, whereas therapeutic is to treat an illness. As listed, there are two types, being SPECT, which is single photon emission computed tomography, and PET, which is positron emission tomography. SPECT measures gamma rays, whereas PET measures positrons. This is just an example of two imaging methods, and they have different requirements for isotopes. Different physical properties are needed for safety and targeting of organic functions to best utilize equipment and transportation in case of the half-life and dose. Chemical is also important, as this can determine reactions and production of the isotopes, and purity determining the cost and ease of the production. Additionally, the dose and desired effect are important to maximize the benefit to the patient, as well as the exposure to the workers both medically and involved in the production of these isotopes. Cyclotrons can be broken down into three main groups. First, here are the small medical cyclotrons, SMC for short. They are also known as medical cyclotrons, PET cyclotrons, and small size cyclotrons. They are categorized by producing a less than 20 megaelectron volt proton beam. They account for a majority of industry production, as due to their size, they can be located much closer to sectors in need of the isotopes, allowing for more efficient use and reduced cost. Next, we have the intermediate energy cyclotrons, also known as the medium cyclotrons for short. They work in the 20 to 35 megaelectron volt range and additionally offer deuteron and some alpha beam potential. Used in production of classical SPECT and novel PET isotopes, the difference being old and understood as classical, whereas novel is newer research-based ones. In some cases, the desired isotope is not being produced, but the parent instead, so that when it decays away, it becomes the desired isotope. Shown on the right is a general size layout to give an idea of how much more infrastructure and space is needed between the small and intermediate. Lastly, we have high energy cyclotrons. They operate at a greater than 35 megaelectron volt range and are primarily dedicated to research needs and other uses, as they are not considered economic for the cost of production of isotopes. They can accelerate and produce beams of protons, deuterons, tritium, alpha, and other heavy ions. This allows for high-energy cyclotrons to produce 68 germanium and 82 strontium. Target materials are the other important part of cyclotrons. They can be broken down into two main categories, being solid and liquid. Solid targets involve plating conducting plates with desired target isotopes. This leads to the material only being a few hundred micrometers thick and put into a geometry setup that makes heat removal from the system more involved due to the lower heat conductivity. This leads to a couple difficulties, as multiple cycles are to be run to get the desired amount of material, as well as stripping from the plate and further separation needs. This has the consequence of needing more handling, which increases the dose to workers, as well as increasing the complexity of retrieval of the desired isotope. These additional steps add to the cost of production, which by comparison is higher than liquid targets overall. The benefits, though, include a higher yield of production. This leads us into liquid targets being the other. They require fewer steps to prepare and handle than solid targets. The added simplicity makes production easier and saves on total production costs. Additional benefits include faster production, not needing to dissolve precipitate materials as it is already in the desired form, and improved recycling of materials up to 90%. However, there are a few drawbacks as well. Overall yield of production is lower than that of solid targets as the solution absorbs some of the beam, creating issues with radiolysis, producing gases and undesirable ions within the solution. These gases produced increase the pressure within the target container that has to be addressed as well.
When looking at using a novel radionuclide for clinical purposes, there are a few needs that must first be addressed. The novel radionuclide must be assessed on what it emits as it decays, how frequently it emits, and how strong that emission is. These physical properties need to be analyzed because if the half-life is too short, the radionuclide may not make it to the desired site before fully decaying. For radioimaging, photon and positron emitters are the most useful, as photon can emit from inside the body while minimizing the damage it causes on that path. And the annihilation event, the positron, produces two useful high-energy photons. Beta and alpha emitters have some use in radiopharmaceutical therapies. Their short range in tissue allows their energy to be directed at specific sites in the body, killing cancer cells without damaging the surrounding healthy tissue. Also, the energy range of the emitted particle needs to be accounted for. For example, in radioimaging, the energy must be high enough to permit the particle to exit the body, but low enough to minimize its damage on the way out. When discussing the chemical properties, the major aspect of a good radionuclide is its ability to undergo labeling, or its attachment to a carrier, which will move the radionuclide to the appropriate portion of the body through natural processes, such as monoclonal antibodies directing radionuclides to tumor sites. Also to be considered are the yield. How much radionuclide can be produced from a quantity of parent material, and purity. If the radionuclide requires a lot of source material for its generation, or is produced alongside toxic isotopes or chemically similar radionuclides with unfavorable physical properties, it is probably not a good selection. With every use of a radionuclide, you are going to incur some dose to the patient. The goal when selecting an appropriate radionuclide is to choose one that minimizes dose while maximizing effect. If the effect requires such a high dose that the patient is in danger of a very negative side effect, you're in a situation where the cure is worse than the disease, and that radionuclide is not going to find its strong use. And the final major portion of the radionuclide selection is price. The less expensive a radionuclide is, the more widespread its use can be, and therefore the financial return on the procedure can actually be quite high. In contrast with the requirements of the clinical side, the industry interests have a different set of criteria for what would make a good novel radionuclide for use in radioimaging or radiotherapy. The paper does state that these two sets of interests do not always align, so it really becomes a test for which set of interests can be more accommodated with each radionuclide. To incentivize their creation, the production of radionuclides cannot be overly complex for their result. Using existing equipment, such as low-energy cyclotrons discussed elsewhere, that are already ubiquitous in their target areas, is always a less expensive option than designing and producing a brand new piece of equipment that is specialized for just one new radionuclide. Also, the fewer people the process requires and the shorter the production time, the easier it is to justify its use. If your process takes 3 full days to complete and uses half of the available staff, the product will be less desirable than a slightly less effective radionuclide that takes one person and an hour to produce. The material that is used as the parent for the produced radionuclide must also be reasonably obtained. As we will discuss later, one of the major driving factors for developing a cyclotron method for producing technetium-99m is that its parent in the milking process, molybdenum-99, is produced in high neutron flux reactors running highly enriched uranium fuels. As those reactors shut down with old age, there is a worry that this nuclide will become more and more scarce and expensive. This would affect the whole pricing chain. Likewise, if the source of the radionuclide is only from a handful of overseas suppliers, political tensions could make their collection difficult, if not impossible, a situation you would want to avoid when it comes to the production of vital medicines. A high molar activity is also important, because it will always be more beneficial to inject the least amount of a foreign material into the body as possible. This will help preclude any toxic effects that could arise from larger concentration, as well as minimizing the cost for the procedure, since less material is required per treatment. We discussed earlier that from a clinical perspective, it is beneficial to have a radionuclide that binds easily to one or a variety of carriers. From an industry perspective, it is even better if that radionuclide does not require a carrier. This limits the amount of resources necessary for the procedure and also reduces the overall toxicity of the procedure. A simple production method is preferred, even more so if portions of that process can be automated. The name of the game is ALARA, so any steps that can be taken to reduce the time workers are exposed to the radiation from a source is a great plus. In addition, the easier and lower number the steps are, the less chance there is for the introduction of errors and mistakes, which could invalidate entire batches of production. Of course, logistics will also come into play. Even if the radionuclide can be produced on site, it must have a half-life long enough to make it from production, through any quality assurance processes, and to the patient with enough energy to still be used. As the production site is moved further and further from the end user, the required half-lives become longer and the initial activities become larger, which could influence the price of shipping and receipt. Finally, no company will invest the time, manpower, and equipment costs for the production of a radionuclide if they do not have buyers lined up for the final product. Before deciding to start production or research into a novel radionuclide, there needs to be a strong list of companies willing to pay for the item. The vast majority of this paper was centered around looking at new radionuclides and processes for making them that are beginning to be seen as viable. As we discussed earlier, the classical cyclotron-produced radionuclides already have a wealth of information and usage statistics. The novel radionuclides presented in this paper are either newly being used, such as gallium-68, have new methods being used for their production, such as technetium-99m, or are in their initial stage of research, where their use has not become common but is being considered, such as palladium-103.
Technetium-99 metastable is a very widely used and useful isotope due to its properties and original sourcing in reactors as a cheap and easy source. As reactors have been closing, production needs have been increasing as well, leading to possible shortages, so alternative methods are being researched currently, as 80% of nuclear medicine procedures currently use this isotope. One such study, when originally being researched as an isotope, showed promising results using 100 molybdenum with a cyclotron to produce, which had high purity and good automated separation efficiency, as shown being over greater than 80%. Iodine-123 requires an intermediate cyclotron in order to produce. Availability is still high even with this, and is useful as it is an ideal for gamma imaging with a half-life that is desirable for metabolic studies. While the cost shown does seem high in comparison, only a small fraction of this liter volume is used in any procedure, bringing the overall cost much lower to those in need. 124 iodine is produced in small medical cyclotrons. While this does make it much more available, it does have a high energy prompt gamma that is not ideal for imaging and increases the dose. It does have an ideal positron emission, though, that makes it desirable for PET scans, and additionally has an Auger electron emission, giving additional use for theranostic use. It also has a production cost that makes it very desirable.
Zirconium-89 has some wonderful properties that make it very useful. Its long half-life both permits easier logistics, as well as its use for studying proteins and antibodies, which require a longer time span of observation for real analysis. It is also very good at chelating with monoclonal antibodies, making it a prime target for its use in immuno-PET studies. Its third major benefit is the lower emitted positron energy, only 0.3955 megaelectron volts, which permits high resolution of radio imaging without a prohibitively high patient dose as a result. Zirconium-89 has 3 cyclotron production pathways, as shown here. In all 3 production methods, the natural element is used as a source target. Naturally occurring yttrium is solely found in the form yttrium-89. complicate production, however, the strontium source requires an alpha cyclotron, which is a very rare piece of equipment. There are also some trace isotopes of strontium in its natural state, which complicate the production, less than 18% strontium-87, 86, and 84 combined. As a result of these hefty difficulties, this method is pretty much theoretical only and not used on any large scale. The deuterium cyclotron method has been proven to produce very high yields. However, the high energy deuterium required to maximize the yield, on the order of 13 to 17 megaelectron volts, is much higher than the range of most small medical cyclotrons, and therefore not as desirable of a method. It's primarily used at research centers possessing high energy multi-beam type cyclotrons. Therefore, the proton pathway is primarily used at smaller medical facilities to produce zirconium-89. On the side, you see a 13.08 megaelectron volt threshold. This is an upper limit, where above that, production of zirconium-88 begins to occur. Zirconium-88 is undesirable because it cannot be easily separated from zirconium-89 and also has a much longer half-life, about 83 days instead of 78.4 hours. This limits its usability in diagnostic processes. When a proton beam of 11.6 megaelectron volts or greater is used, there's also the co-production of yttrium-88. This nuclide can be separated with chemistry processes. However, as described before, the more steps added to the procedure, the less desirable the entire process is. As the energy of the proton beam is lowered, however, the yield of zirconium-89 also lowers. Proton beams less than 10 megaelectron volts produce insufficient quantities of zirconium-89. Therefore, a balancing act of targeting just below 13.08 megaelectron volts and 11.6 megaelectron volts, while also maintaining above 10 megaelectron volts, is desired. The best yield process reported is with an 11.6 megaelectron volt beam. Generates about 14 to 16 megabecquerels per microamp hour with high purity. Therefore, about 1.4 gigabecquerels of zirconium-89 can be produced over the span of 3.5 hours via this method. There's also been studies into utilizing custom targets to be produced instead of just using natural yttrium. These targets use water cooling and variable yttrium foil thicknesses welded together to produce a yield of 49 megabecquerels per microamp hour with a 90% separation efficiency. Therefore, about 2 gigabecquerels of zirconium-89 can be produced over about 2 hours, which greatly reduces the required cyclotron usage time, freeing it up for usage to produce other required radionuclides. There has also been research into custom liquid targets, but they result in a much lower yield and therefore are only used where solid targets cannot be utilized due to workspace limitations, and the required zirconium-89 to be produced must also be low. Copper-64 began being utilized in the late 1990s as a non-standard radionuclide for PET. Cyclotron production of copper-64 uses a nickel-64 proton-neutron copper-64 production pathway with a solid nickel target. The maximum copper-64 yield occurs at a 10 to 15 megaelectron volt proton beam, but requires a beam of at least 2.5 megaelectron volts to function. These values can be easily obtained with current small medical cyclotrons. Most of the solid nickel-64 targets have a gold disc base with electroplated nickel-64 on the exterior. Maximum production can be achieved with an 8-hour beam with 40 microamp currents, producing about 185 gigabecquerels of copper-64. However, that much copper-64 is not usually needed in one production run, so shorter times are often used. Current research into the production of copper-64 is focused on further automation of the process, as well as the development of additional carriers for copper-64. We will discuss the advantages and disadvantages of this current production process in the next slide. An alternative method with zinc-67 as the parent has been proposed and is functional. However, there are some purity problems associated with this process. Additionally, a liquid target is in development, which would be useful for further automation of the process. Experiments have currently produced a yield of about 77%, which could be made even better by increasing the nickel-64 concentration in the liquid target. There are quite a lot of pros to the use of copper-64. Its half-life of 12.7 hours is sufficient to permit shipping as a viable logistic pathway. It has few gamma emissions, 0.5% yield with a 1.346 megaelectron-volt gamma, and low positron energy, 0.27821 megaelectron-volts, which permit very high image resolutions. Current production methods have a high yield and high purity result, and these methods have been established strongly over the past 3 decades. Another aspect of copper-64 is its release of a beta, 38.5% yield, 0.1907 megaelectron-volts, which could in theory be used in theranostic methods. However, further research into this field is required. Copper-64 chelates very well with a variety of carriers. However, this pro is slightly overshadowed by the fact that zirconium-89 has a very similar chelation ability, and zirconium-89 has an even more desirable half-life, and is less expensive to produce. Some disadvantages associated with the use of copper-64 include the low abundance of its parent, nickel-64, therefore requiring a high level of parent enrichment prior to utilizing. This results in added complexity and added cost in order to produce. Current solid targets of a gold disc with electroplated nickel-64 are effective, but require care during the handling process. Improper handling of these discs can disrupt and cause additional surface roughness of the plating, which makes its use less efficient. Further, in order to continue usage of the discs and recycle the parent material to the greatest extent possible, on-site electroplating and recycling processes are required. This is costly and difficult, making production process prohibitively expensive for smaller operations. As discussed in the previous slide, maximum yields are produced when targets are irradiated for 8 hours. Every hour you spend producing copper-64 is an hour the cyclotron cannot be used to produce another radioisotope. Thus, the process becomes more expensive. The final major downside with copper-64 production is that the process does not have a current level of automation to reduce operator exposure drastically. Until automation of the process can be handled more effectively, the exposure of the operators must also be factored into the cost. There are 3 gallium radionuclides which are useful in nuclear medicine applications. These are gallium-66, gallium-67, and gallium-68. Gallium-66 is the least used of the 3 because it has a very high energy positron, 1.904 megaelectron volts, which creates a high dose for the patient and lowers the resolution of the produced images. Gallium-66 also produces 2 high energy gammas during its decay, 37% yield of 1.039 megaelectron volt and 23% yield of a 2.751 megaelectron volt that further exacerbate the dose received by the patient. Thus, only gallium-68 and gallium-67 are routinely used. Gallium-68 is produced in a germanium-68 gallium-68 generator. They have a short half-life, 67.7 minutes, which prohibits their transportation from a central production facility to an end user. But the germanium-68 parent has a long half-life of 271 days, so gallium-68 just gets produced on site. This lower half-life is beneficial in that it lowers the dose to the patient from the procedure. Gallium-68 has been produced as a part of various kits and functions extremely well as a radiotracer. Gallium-68 has been recommended to replace indium-111 in neuroendocrine tumor SPECT imaging in the UK. The parent radionuclide, germanium-68, is currently produced in cyclotrons, with a natural and 69 gallium proton-neutron reaction producing germanium-68 channel, using a beam above 20 megaelectron volts. As the use of gallium-68 increases, the desire for alternative methods for germanium-68 production that do not require specialized tooling to handle a high heat transfer over a time span of weeks is being investigated. Small cyclotrons can produce gallium-68 by bombarding natural zinc and zinc-68 with protons. This is the 1 barn cross-section with 11 to 14 megaelectron volt threshold shown in this slide. This method is less useful than the germanium-68 gallium-68 generator because of the complex solid target development and handling, the required enrichment process of zinc, and the creation of inseparable impurities of gallium-66 and gallium-67 during production. Liquid target research has thus been in development, focusing on the zinc-68 to gallium-68 proton-neutron production channel. The optimal gallium-68 production cross-section unfortunately occurs at 12 megaelectron volts, which is also the threshold for gallium-67 production. By dissolving zinc-68 in nitric acid first, Pandy et al. 2014 have claimed to produce radiochemically pure gallium-68 for about 2 to 4 patients over 1 hour of cyclotron operation. Alves et al. Are also looking into the creation of a liquid target and have boasted 40 gigabecquerels of gallium-68 produced over 45 minutes with a 45 microamp proton beam. The resulting product also was produced without any long-lived impurities. Gallium-67 is an alternative for SPECT imaging, being used most extensively as gallium-67 citrate in tumor and infection detection. The most commonly used method for gallium-67 production is through irradiation of solid zinc-68 or zinc-67. The zinc-68 production requires a proton beam exceeding 10.3 megaelectron volts, with highest yields around 21 megaelectron volts. This method also produces the chemically similar gallium-68, which must be removed via decay prior to the usage of the gallium-67. Since the half-life of gallium-67 is much longer than the other isotopes, at 78.3 hours, it can be purified out from the other isotopes merely through decay, and as such, natural zinc can be used instead of a highly enriched source. The zinc-67 channel for gallium-67 production is viable for small medical cyclotrons, since the threshold energy is only 1.8 megaelectron volts. However, this method requires the much more expensive enriched zinc-67 and requires staying below 13 megaelectron volts to preclude gallium-66 formation. This method has been relegated to theoretical as a result, due to the ease and cost of the zinc-68 method just requiring the decay of impurities. A single cyclotron producing via the zinc-68 channel can adequately cover an entire region's gallium needs.
11 lanthanide is another intermediate cyclotron-produced isotope. Production is easy with its 1000 barn cross-section, but leads to impurities of cadmium and tin, which, thankfully, are separable. Commonly it is used in SPECT imaging due to its low energy and high intensity. Having a 2.8-day half-life, it is useful for study of organs and internal medicines in an in vivo study. It is shown that it could be produced in small medical cyclotrons as well, using 111 cadmium that produces no impurities of concern, but there's no literature on this experimentation or shown interest among current small medical cyclotron users.
Yttrium-86 can blame the attention it has received on its widely used isotope, yttrium-90. Its decay positrons are low intensity and high energy, 11.9% with half a megaelectron volt, 5.6% with a 0.6811 megaelectron volt, and a 3.6% yield with a 0.8833 megaelectron volt, for example. However, yttrium-90 is purely a beta emitter, and as such has very limited imaging uses. By using a mixture of yttrium-90 as a radiotherapeutic isotope and yttrium-86 as a radioimaging isotope, a single carrier can be utilized to deposit both isotopes in the region of interest, allowing simultaneous therapy and imaging. A strontium-86 parent can be used for very high purity yttrium-86 reaction, as shown in the slide. However, this requires a highly enriched target and has to compete with strontium-88 channel, which can be enriched for a much lower cost due to its natural abundance. However, the latter process requires a much higher energy proton beam of 33 to 44 megaelectron volts, which excludes small medical cyclotrons from participating, and furthermore generates yttrium-87M and yttrium-85 impurities. As a result, the strontium-86 method is the more commonly used pathway. The major impurity of strontium-86 channel is yttrium-86M, which in turn decays into yttrium-86 in a half-life of 48 minutes and is therefore not considered an impurity. The most effective target determined through various experiments has been a strontium oxide target with a 2 microamp 14.5 megaelectron volt beam for 2 hours, creating a 166 megabecquerel per microamp hour yield. Current liquid target experiments have focused on strontium nitrate salt dissolved in water. The resulting yield was much lower than the solid target experiments. However, the concentration of natural strontium in that liquid was also much lower, and thus the efficiency could be increased by raising the concentration of strontium.
44 scandium has a vast list of methods for production making sourcing very easy to come by. Currently it requires an intermediate energy cyclotron from 28 megaelectron volt alphas or 16 megaelectron volt deuterons. In vivo generation, which is where it goes through its half-life process within the body to generate the desired isotope, allows for more complex combinations of properties for medical use. Scandium has been creating interest for PET image as it holds similar body absorption as deuterium and yttrium. This is because of the low positron energy and the beta branching, on top of the physical properties that allow it to be absorbed by certain organs. Another benefit is the cost of production, as targets and intermediate energy cyclotrons are within desirable budgets of users and producers. Current research has shown that scandium could be a possible theranostic agent if paired for research use for peptide imaging, labeling of antibodies, and also labeling of small protein chains.
The final portion of the paper is devoted to other radionuclides under research. They are listed here, however their use and research are limited due to the lack of developed applications, scarce nuclear data, or prohibitively high initial investment requirements. Further development in this field would require a high initial cost, and thus, in accordance with our initial discussion about industry and clinical requirements, are not likely to be developed in the very near future. The table shown above comes directly from the paper being discussed, and shows a comparison of the radionuclides presented in the lecture. If you are interested in the medical application of novel radionuclides, this table will be of great interest to narrowing down potential candidates for research. Thank you all for your time, and we welcome any questions you may have in regards to this presentation in the chat.